Hello everyone. In the past lectures we have used a lot of times conservation laws for mass, for momentum, both. And especially for the lecture that I gave for Poisson flow, for pressure-driven flow across parallel plates or tubes to get the sense about permeability in a fractured system or in a kind of a bundle of tube theory, which is R²/8, I've used a lot of conservation laws. Conservation laws are extremely important. And so I have used them within my lectures so far, and you have been hopefully be able to follow them. I thought that I would dedicate a series of lectures only for conservation laws to make sure that all aspects related to them are crystal clear to you. We start with mass balance, to momentum balance, and eventually to energy balance. So let me start obtaining the conservation laws because they are crucial and very important for us as engineers because they allow us to translate the nature into mathematics. And then by using thermodynamics, constitutive laws, boundary condition, initial condition, we can actually solve a specific process, whether in free flow, in atmospheric flow, in flow around an aircraft, etc., or in the subsurface, geothermal or hydrogen storage, CO2 storage, or aquifer flow in the subsurface formations. They are very, very important for us to understand because whenever I want to model any process and I look at it, the first thing I ask myself is, what are the conserved quantities? And I start with conservation laws all the time. So let's start with it. Imagine you have a stream of flow. I have a stream of flow that is happening and I am observing it. So that's a stream of flow that is happening in a system, a river flow in the subsurface, wherever it is. I'd like to describe conservation law for this system. It's important for me to know that conserved quantities are per mass intensive quantities, and for a specific system, when I integrate it for all the amount, that is an extensive quantity. So an intensive conserved quantity shall be called, let's say, X, which is the conserved quantity per mass. So this is per mass. There is a theorem for the transport of this conserved quantity, which says the change of the conserved quantity should balance the source term. If there is no source term for that quantity, it should not change. So then we start with a theorem for the transport, which is called Reynolds transport theorem, RTT in short, Reynolds transport theorem. What does Reynolds transport theorem say? It says the total change of your conserved quantity in an intensive way, so ddt of the entire change of X, since X is per mass, I multiplied with density, which is mass per volume, and per mass quantity will be per volume quantity, y multiplied with it. So rho x can be said as x prime. X prime, then it will be per volume. X is per mass. So this x is per mass. And x prime is per volume. Integrated over the entire volume of the system, so system volume, that is the total change of your quantity. Per volume multiplied by volume will be the entire amount of that quantity. It can be mass, it can be energy, it can be momentum, right? So that's the Lagrangian perspective, which is the total material derivative. Material derivative, which is d dt. The d is straight. That is a Lagrangian perspective, which is you are on the stream of flow and you are traveling with the flow. You are on a boat with the flow traveling. There is another perspective in fluid mechanics that observes the stream of flow from outside, a fixed point. So it will fix its observation and let the flow happen while you are fixed with your position or your control volume, the fixed control volume, fixed location. Now, this one will be equal to the change of the amount of x in your control volume, so that will be over the volume of control volume, let's call it omega, and I call the boundary of the control volume as partial omega, so that's the boundary. Over omega, rho x dv will change because amount of x, amount of density may change, if it's compressible flow, for example. But that's at a fixed location, so change over time of that rho x, so that's the change over time at a fixed location, so that is change at the fixed position or location, which is your control volume. And then, since you are fixed with your position, you are not streaming through the flow, you will see there is a flux of that x coming in and going out. So there is an integral over the boundary of your control volume of the amount of x that you have, your conserved quantity per volume, and flux of it inside your control volume. This is the surface, and un is the normal vector, n is normal vector to the surface of your control volume. So that is n, that is n, this is n, and this is n. So n is normal outward. And if you have a stream of flow that comes and leaves, you see that u in the outflux is parallel to n outflux, so then outflux is positive and influx is negative because incoming flux is in the opposite direction to the normal direction of n, and in that sense the dot product of them will be negative. Obviously, u velocity can have a multidimensional vectorial space. We just get the projection of u across the surface. The other projection is rotational one, and that doesn't matter for us because it does not leave us. It's not the mass that we will lose or energy that we will lose or momentum. So this part is the flux, and net outflux of my conserved quantity. So I forget about of because it's clear that it is the net outflux of my rho x. Yeah? And that's also at the boundary, across the boundary of my control volume. This is now, in a very, very generic way, translation of total material change to a fixed position change, which is and this is Eulerian system. So this is Eulerian system. The other one is Lagrangian system, because here you fix your position. Now what I would like to do is I would like to write this for mass balance. Right? This is just letting me know that the total rate of change of something is related to the fixed position of control volume, change of the property, and the flux net outflux of it. Right? So let's write it for mass balance. When I write it for mass balance, my x, which is mass per mass, is 1. My x prime, which is the per volume, is rho times 1, which is rho. So depending on what do I write, I use this. So that means that my relationship will be the total change of my mass in a Lagrangian system will be rho v. That will be change over time across my control volume of rho dv plus in a control volume, and there is obviously no sign of boundary. This is just integral over control volume plus integral over the boundary of my control volume, rho and then I have U dot N ds. Now mass, the total change of mass is 0 if there is no source. If I have a source there, I also have over my control volume rho Q dV. And this rho is kilogram per cubic meter, and my Q is intensive Q, which is volumetric production rate over volume. So that will be what? It will be the 1 over s second, right? And then I have here d volume, which is cubic meter, right? Q dV is the volumetric production that I have, right? And that really matches here very well because this is rho dV over time. So 1 over second is here. See, this is 1 over second. This is again kilogram per cubic meter. And this is cubic meter, right? So then you have again the unit that you will get is 1 over second, which is again here. And then you have kilogram per cubic meter here, and this volume here is cubic meter, and that's also exactly the same as we have. Now, this integral over the surface of my control volume can be used by divergence theorem as the integral over the control volume of divergence of rho u, d volume. That's why divergence operator mathematically means net outflux of the quantity in the front of it. So divergence theorem says the integral over closed boundary of a flux of a term is divergence of that flux over the entire volume. So what I get at the end is very interesting because I can then say my entire equation will be d dt of over control volume rho dv plus over control volume divergence, which is net outflux of rho u dv equals rho q dv over the entire volume. And I can just put them all in the left-hand side and factorize the integration operator because for all of them is the same. So I get integral over volume. The first term is d dt of rho. The second term is divergence of rho u. U is a vector. Then I have rho q, which comes to the left-hand side. It will be rho q. And if I take all of them, dv, this is 0. If integral or summation of something over the volume is 0, and it is holding for any omega you take, any omega, the term inside must be 0. There is no other way that it can have positive and negative value that the sum is 0. Because then you can refine your omega and then only encapsulate the positive side and then it is no more 0. So this is telling us mathematically that it can only hold if d rho dt plus divergence rho u minus rho q is 0. And that's mass conservation in the most generic way. So units, Q is 1 per second, rho is kilogram per cubic meter, and that's all. The rest is very clear. U is meter per second. Divergence operator is 1 over meter, and density is already known to you, which is kilogram per cubic meter, and the same here as well. This is ddt is 1 over second, etc. Where is the meter cubic? Where is the volume? It's the dv here that we have dropped it. It cancelled it. So when you multiply it by volume, it becomes a volumetric equation. At this moment is kilogram per cubic meter times 1 over second. It's a very strange unit. So now, This is my mass balance, and I did not do it for porous media yet. This is for free flow, because I assume that the entire X is available here to be stored here. But if you have, so that's the free flow. If I have porous media, then not all of the space of control volume is available for me for flow and storage of X, etc., but the porosity part of it. So it will be porosity rho over time plus divergence of rho. Now it's porosity times velocity of the fluid, which will be the Darcy velocity. So that's the Darcy velocity. That minus rho Q is 0. Or I can put it equal rho Q. That doesn't matter, I can write it, but just to be the same. So this is porous media, this is free flow. It's only that here U Darcy is porosity velocity of the fluid. And that's because if I have a cross section like that and I have grains here, that will stop, obviously. The flow is only for the inside of the porous space and not through the grains naturally, because this is the solid part. Then I know that fluid is only flowing through these kind of void space. So the area, cross-section area of the porous space times the velocity of the fluid, or U of the fluid, doesn't matter. Since I use U fluid, let me also use U fluid. So that's U fluid is the total cross-section area times the velocity average Darcy. And that means U Darcy is a cross-section of pore over cross-section total times U fluid, and that is my porosity. And therefore U Darcy is porosity UF, and that's why I put U Darcy here in my mass balance. So that's for porous media, and that is for free flow. Now remember one thing we did. Either one doesn't matter, porous media or free flow doesn't matter. If you're solving for incompressible flow, and then assume that also porosity is constant if you are doing it for porous media, so then incompressible flow and also incompressible system, flow and solid, or porous media, so porosity is constant and density is constant. Solid incompressible is not exactly porosity constant, but just me say that incompressible flow and rock. Flow and porous media. Then ddt will be 0, so ddt of, let's say, rho phi will be 0 because they are constant. Obviously ddt of rho will be also constant. If you do free flow, that will be constant. And then you get, for example, for free flow or Darcy flow, doesn't matter because the forms are the same. The only matter is that for free flow, this is U of fluid. For Darcy, it's U Darcy. You get divergence, rho U equals rho Q. And since rho is constant, you can cancel rho, and that gives you divergence of velocity is Q. Which means if you have no source term, no production, no injection, then Q is 0, and therefore divergence of velocity is 0. This is a key equation of mass balance for incompressible systems. Divergence U is 0. In one dimension, for example, in Cartesian coordinate of x direction, it means ddx of ux is 0, which means velocity is constant. In two dimension, for example, again in x and y direction, it means dux dx plus duy dy is 0, which means the change of velocity x direction in x direction, the change of it should balance the change of the y component in y direction, which means if it is accelerating in x direction, it must decelerate in y direction. In general, divergence is 0. In multidimensional systems like 3D, I hope it is typed and printed here, you have x, y, and z direction. That means, I'm writing it here for you, it will be ddx of ux plus ddy uy plus ddz uz is 0. That's the divergence operator. Divergence means ddx of x component plus ddy of y component plus ddz of z component. That's divergence. Divergence of a vector is a scalar. This is a vector by itself. This is vector. Dot product makes them to be a scalar. So that's why in x, y, z, you get ddx of the component in x direction, the vector value in x direction, ddy of the y value, ddz of the z direction value. In radial coordinate, you do similar as well. In radial coordinate, you get to know what's the divergence operator in radial coordinate. You can write it also for radial coordinate, because then it is like, let's say if I have r and z coordinate, which is radial and cylindrical, let's call it cylindrical coordinate, which is only r and z, for example, 2D, then you get to see that the divergence of u will be 1 over r ddr rur plus duz dz of the ruz. So that's ddz of uz should be the right term. So this is the divergence operator that can be written in radial coordinate, which is r and z. It can be written in many other coordinates that you like to have, like a spherical coordinate in which theta also comes, and therefore you will have a term that would represent your theta component and entity, which would be 1 over r dd theta of u theta, etc., whatever it is. So whatever you do is that the great thing about the divergence operator notation is that what you will do here is, in this divergence, you go and search if you are in Cartesian system, which is x, y, z, or 3D here, or you are in x and y, for example, 2D, or you are only in x, which is 1D, or you are in r theta z, which is 3D, or r theta or rz, depending on what system you have, or you have only r. You write what the divergence operator does to your velocity. In Cartesian system of x, y, z, u will be ux, uy, uz. That's your vector of velocity. In radial coordinate, your velocity will be ur, u theta, uz. And that's why when we did the Poiseuille flow, we used Navier-Stokes, which is the momentum balance, and I'm coming back to it in the next lecture to explain to you how do we get from Reynolds transport theorem the Navier-Stokes equation. That's very much fun to observe. So this is all about it. And what else I can say is that for porous media, when I have where is it? My porous media is here. This is my porous media equation, which is this, and I have divergence rho u and rho q. I know that u Darcy is also proportional to the pressure by Darcy's law, which is minus k over viscosity gradient of pressure or potential. So I know that this is proportional, the u Darcy is proportional to the pressure gradient through Darcy's law. For free flow, the proportionality of velocity to pressure gradient comes from momentum balance, which is Navier-Stokes, which is the topic of the next lecture. Here also Darcy's law replaces the momentum balance. For mass balance, you see that just writing the material change with the fixed position with Eulerian system, so changing Lagrangian perspective to Eulerian system, then we wrote down for intensity property related to mass, which is mass per mass is 1, or if you write it per volume intensity property, it will be density, and so you will write down your balance equation that eventually becomes this key equation of ddt of density, divergence rho u minus rho q is 0. And that for porous systems, you need to account for porosity perspective. Porosity portion is available for flow and for storage. So you do porosity density, and here porosity U fluid will be U Darcy, and then you get the key equation of the mass balance for Darcy's equation. One last note, my friends, before we say goodbye for this lecture is we wrote them down for single phase flow. Single phase flow. I did not yet introduce multi-phase flow because we can write mass balance for multi-phase flow when we have CO2 and brine. And then you will get a bit of extra terms here too. This is for single phase flow, which is very relevant, especially to atmospheric flow and other flow as well, free flow as well. But that's the most essential equation that we have. And next we do the momentum balance, then energy balance, and then we go on to a lot of other courses to come, including multi-phase flow. Thanks a lot for the attention. I hope it's generally clear, and we move on to momentum balance.